Alright, so in this video I'm gonna be explaining another important article about domain adaptation. The title of this article is Generalizing to Unseen Domains via Adversarial Data Augmentation. This paper in 2018 from Stanford University. We are concerned with learning models that generalize well to different unseen domains. We consider a worst-case formulation over data distributions that are near the source domain in the feature space. Only using training data from a single source distribution, we propose an iterative procedure that augments the dataset with examples from fictitious target domain that is hard under the current model. We show that our iterative scheme is an adaptive data augmentation method where we append adversarial examples at each iterations. For softmax losses, we show that our method is a data-dependent regularization scheme that behaves differently from classical regularizers that regularize towards zero. On digit recognition and semantic segmentation tasks, our method learns models improve performance across a range of priori unknown target domains. We wish to learn a system that can perform uniformly well across multiple populations. We develop methods that can learn to better generalize to new unknown domains. We consider the restrictive setting where the training data only comes from a single source domain. Inspired by a recent development in distributionally robust optimization. This is an important field in machine learning. Distributionally robust optimization. So we consider the following worst-case problem around the source distribution. We minimize the supremum of expectations. And this D is a distance metric on the space of probability distributions. Because if we have a source distribution P0, we want to go all the distributions that around this P0, for example, P0 is just a dot. This distribution is just a dot. Assume it is just a dot. But you want with the radius of rho, we want to select all of the distributions. And among them, we want to minimize the expected loss. The worst case, we minimize the worst case. When we say supremum, when we are minimizing the worst case of expectations over all family of distributions that are within distance rho, within radius rho. So we propose an iterative procedure to solve this problem one. We need an iterative procedure. So each iteration of our method uses small values of rho, and we provide a number of theoretical interpretations. First, we show that iterative algorithm is an adaptive data augmentation method where we add adversarially perturbed samples at the current model to the dataset. Our adversarially generated samples roughly correspond to Tikhonov regularized Newton steps. And from a practical viewpoint, a key difficulty in applying the worst-case formulation that I showed you is that the magnitude of the covariate shift rho is a priori unknown. And we propose to learn an ensemble of models that corresponds to different distances. In other words, our iterative method generates a collection of datasets, each corresponding to different inter-dataset distance level rho, and we learn a model for each of them. At test time, we use a heuristic method to choose an appropriate model from the ensemble. This is a substantial body of work on domain adaptation, which aims to better generalize to a priori fixed target domains whose labels are unknown at training. This setup is different from ours in that these algorithms require access to samples from target distribution during training. But domain generalization methods that propose different ways to better generalize to unknown domains are also related to our work. These algorithms require training samples to be drawn from different domains, not a single source, a limitation that our method does not have. In this sense, one could interpret our problem setting as an unsupervised domain generalization. The worst case formulation that I showed you, expectation of supremum of that loss that I showed you over domains around the source, we had P0 minus P less than rho, for example, radius rho. That formulation around the source P0 hinges on the notion of distance that characterize the set of unknown populations we wish to generalize to. Conventional notions of Wasserstein distance used for adversarial training are defined with respect to original input space, which for images corresponds to raw pixels. Since our goal is to consider fictitious target distributions corresponding to realistic covariate shifts, we define our distance on the semantic space. Before properly defining our setup, we first give a few notations, letting P the dimension of output of the last hidden layer, and theta, so theta T is the set of weights of final layer. This one is just the final layer. And theta F is the rest of the weights of the network. And we denote by G of theta F, which is parameters of the rest of the network, the output of the embedding layer of our network. For example, in classification, M is the number of classes. And we consider this softmax, where theta is the J's column of classification layer. Wasserstein distance on the semantic space. Consider the following transportation cost, this C in the theory of optimal transport that French mathematician was talking in his book, that theory of transportation, optimal transport, the cost of moving mass from Z and Y. I remember that name, Cedric Villani, who is the advisor of Macron as well. And he has a great book on optimal transport, but you don't need to learn everything. You just need to know that we have this transport from cost of moving mass from Z and Y to Z prime and Y prime. The transportation cost takes value infinity for data points with different labels. Since we are only interested in perturbation to the marginal distribution of Z, we now define the notion of distance on the semantic space. For inputs coming from the original space, we consider the transportation cost defined with respect to the output of the last hidden layer. And C theta measures distance with respect to feature mapping G. For probability measures P and Q, both supported on X and Y, this pi is just their coupling. So this pi here is just their coupling, meaning measures M, and P and Q. So we define our notion of distance using infimum of this expectation of the cost between x and y and x prime and y prime. Armed with this notion of distance, and we now consider a variant of worst-case problem where we replace the distance, our adaptive notion of distance, defined on the semantic space. But you know that this supremum is intractable, so we just use this Lagrangian relaxation with penalty gamma here, the penalty. So we relax the problem. This is a technique in optimization. So we run the minimax procedure k times. We sample uniformly, then update. And here we are updating x. So for any distribution Q, we have this relation. This is a lemma that the supremum of expectation of loss of minus gamma v is expectation of phi. And phi is just, we have defined it as, we call it the robust surrogate loss, which is supremum over this loss minus gamma c theta. And c is the cost transferring from x and y0 to x0, y0. And then we have the iterative training procedure where two phases are alternated. The maximization phase, where new data points are learned from computing the inner maximization problem, and a minimization phase, where the model parameters are updated according to stochastic gradients of the loss. The hyperparameter gamma, which is inversely proportional to rho, the distance between fictitious target distribution and source, controls the ability to generalize outside the domain source. So to select the best model at test time, we select the model with greatest softmax here. Now they give an interpretation of the augmented data points in the maximization phase. Remember that we had two phases, maximization and then minimization, that we alternatively train both of them, made several times, like expectation maximization framework. So this implies that the adversarially perturbed sample is drawn from a fictitious target distribution, where probability mass in Z0 was transported to this G hat nu. And also they have the theorem that the distance is upper bounded by these constants. And the rest of them is conclusion and future work. We study new adversarial that learns to better generalize across a scene, define ensemble methods to exploit this technique. This is in contrast to domain adaptation methods, which require a sufficient number of samples from a known, priori fixed target distribution. So that's why they call it unsupervised domain generalization, because they are not even accessing the target samples. Of course, we never use the labels of target, but we are not even using the samples itself of the target.